Okay, we're going to continue today with chi-squared. So take a deep breath after the quiz, but these quizzes are simple anyways. It's like just succeed for itself. So I'm gonna make my quiz a little bit more difficult. Who's been working? If you don't feel distracted here in the front, if it's in the front, otherwise you can sit in the back, whatever works best. Okay, so we have 51 minutes. 51 minutes to get through chi-squared. That's going to be a little tight, but I think we're going to do this in an efficient manner. And if worst comes to worst, we're going to cover the little time on Wednesday. Good, chi-squared. So chi-squared is now a new class of statistics. It's non-parametric statistics that basically do not have to fulfill those assumptions that a parametric test has to fulfill, which is, you remember, randomly sampled, linear relationships, normal distribution, and homoscedasticity. Those are the 4 assumptions that you have to have in a parametric test. In a non-parametric test, they don't have to make these assumptions. That puts them kind of in a very different spot, and they're particularly used when it's small samples, really small samples that are less than the 30 degrees of freedom, or the 30 of sample size, beyond which you usually get away with parametric tests. It's also used in a very specific setting where you basically have a categorically or nominal variable. So a categorically variable, and you're analyzing this as a function of categorically variable. So it's a dependent categorically and an independent categorically variable. And that's the reason why the chi-squared test, as the only non-parametric test of this class, made it into the curriculum, because it is a peculiar kind of situation that you would use this test. And when you remember, we had pretty much we discussed 2 different scenarios. We had scale-independent variable and scale-dependent variable that would prompt you to think of correlation or regression. If you have a scale-dependent variable and a nominal independent variable, you would think of a set test. If it's for a population, or you're comparing a sample mean to a population mean, you think of all kinds of t-tests, and of course also of ANOVA. You have scale-dependent variable on the y-axis, and you have a nominal independent variable on the x-axis. So now you have a categorically dependent variable and a categorically independent variable. And the way you will be organizing this is basically now in what is called a contingency table, or 2x2 table, or 3x6 table, depending how many rows. You will give them a numerically label, but basically it's called a contingency table. So the simplest form of that, basically, we will discuss now in our goodness of fit analysis that we will do first, and then we'll do a classical test for association with a chi-squared. So, so you use this when the dependent variable is either form of categorical variable, or when the sample size is small and the population is not normal. So confidence intervals and effect size measures are not typically available for nominal or ordinal data. It's not necessarily true, because you can kind of estimate them, but that's again beyond the scope of this class. They do notably, because they don't make these assumptions and arithmetically not as strict as parametric tests, they do have less statistical power. Also because the sample size is substantially lower. So you can do non-parametric tests actually in very small sample sizes, and that's also one of the triggers to actually use non-parametric tests. As a consequence, you're more likely to commit the type 2 error. As a quick recap, type 2 error, keep in mind, type 2 error, and remember that 2x2 table that we discussed in that context. So you basically have a type 2 error when you have in truth an effect. So the null hypothesis is actually false, and you do not sense this difference. So you're not rejecting the null hypothesis. The reason that will make you think that could happen is most likely the sample size. Sample size, too much variability, not enough difference between your 2 levels of the independent variable. So that will prompt you. So it's basically, it's less statistical power. all the factors that lead to statistical power will then increase the probability for type 2 error. And also remember, it's like if you don't would need to reject the null hypothesis and you don't, rejecting the null hypothesis comes at a probability of 100% because either you reject it or not. And if you don't reject it, although you should have rejected, that's the type 2 error. And 1 minus the type 2 error, this probability is the statistical power, which is estimated a priori before you start your research. Then you have obviously also type 1 error. With the type 1 error, that's basically where you are rejecting something that you shouldn't have rejected, most likely due to subsetting, exclusion of outliers, or repeated sampling and biased sampling. Okay, so that's this when you would think of non-parametric tests. Any question? Then we can actually look at the two most commonly used chi-squared statistical tests. It's called chi-square because that's the new comparison distribution we're going to be discussing. It is the chi-squared distribution. It's comparable to the F statistics, a unimodal right-skewed distribution that basically has a critical value. It's basically, again, one-sided. So it's a one-sided comparison distribution. So you basically, once you exceeded a critical value on your chi-squared distribution, you're rejecting your null hypothesis. And what the implication of that is, we'll discuss in a second. So chi-squared test for goodness of fit is where you have one nominal variable. So you have one categorical variable with two different levels that you're basically comparing against each other. With a chi-squared test for independence or the inverse association, you have two nominal variables with two different levels that basically leads you to a 2x2 table at the very least, or the 3x6 table as the one, the 3x2 table that we'll discuss today. Good. The 6 steps of hypothesis testing, the same as we discussed in the past. We have infinite population. We will determine the comparison distributions, the chi-squared distribution. We will make our assumptions, which there are not that many. We state the hypothesis, which basically says that there's no association between the nominal variable and the two levels. We determine the characteristics, critical values based on the degrees of freedom of our observation, and the chi-squared table, which is to be found in the module in your canvas. Then we calculate test statistics, and we decide based on the critical values that we've determined from the chi-squared table. And okay, so you basically, you have always two populations at the very least. So you're comparing two populations against each other, which basically are determined and categorized based on the two levels of your independent variable. So you basically, you have then matched frequencies between these two levels, and you're comparing these two levels to what you would expect. And what that means, we're going to get to in a second. Because, well, it's actually easier to show you that in the example. That's again one. Yeah. So if you open the example that we will be discussing today. So there was research done, which is kind of this interesting research. I'm not sure who's doing that research. But again, okay, so we have 52 elite youth players in Germany. So since the World Cup just concluded last Sunday, I hope you all watched, so basically it's a soccer example. So we have 52 elite youth players in Germany that were born in January, February, or March, whereas only 4 of these elite players were born in October, November, or December. So you have basically the hypothesis here is, or the research question is, does it make a difference which year, which month of the year were you born, and the probability of you moving forward to become an elite soccer player, which is a debatable hypothesis, but actually there are some theories the authors have put forward. So there's actually real research that was conducted, and so there are theories where that could be the case. Zodiac signs being one of them. Okay, but basically what you would be doing now is, so you are determining now, so early in the year were 52 individuals that were born. And then you had later in the year, you had only 4. So you have here your observed counts. So that's just a count. And for the quizzes, what you will need to understand is how do you translate what's being given to you, what is provided to you, into such a table. So you have observed versus later in the year. If you want to know now whether there's an association between being an elite youth soccer player and the time of the year, you would need to distinguish between your observed counts and what you would have expected if there were no association. And that's the key, because you need to understand what is expected. And this is why I wanted to go to this example right away, because it's easier to think that through in such an easy example, because if you expected that there is no difference, so that's your null hypothesis, what would the distribution be? This is in total 56 elite youth players. If there were no difference and the probability of this playing a role would be null, you would have an equal distribution between those. So your expected would be 50% in each of your 2 levels. So this.
How it is? Is that always how it is? Like if there would be no effect, then it's split?
It is equally distributed amongst the levels of your independent variable. And this basically would render this to be 28. So now you have observed versus expected. So there's a difference that you see with the naked eye already. If the chi-square basically tests for an association between these 2 variables, the observed elite soccer player and the count of those, and the distribution amongst this one nominal, this nominal or categorical variable. And I just meant to show you this because that kind of makes it easier to understand what we're actually looking at. So we have 2 populations. We have 2 populations with respective frequencies and these 2 different levels of your categorical variables. And you're matching those frequencies now with an expected count according to the null hypothesis. So these 28, you're testing whether this is actually significantly different from the 28 in each group, which would have been expected. And you're comparing, so you're calculating based on that, you're calculating the so-called chi-squared that kind of takes into account the difference between those 2. And if the chi-squared is beyond a certain critical value, you will reject the null hypothesis that there's no association. Yes?
So even though it seems like an example that they are so different, like the observed is very different than expected, you can't just say like, oh, so of course there's an effect. You have to see if it actually matches the critical value.
Exactly. So you would need to test this to determine statistical significance. Exactly. So just those of you who did homework 2 already, there are some examples where you have like just such an enormous difference, such an enormous set score, I think was to be calculated for that, that kind of made it absolutely implausible that there would be really no effect of the independent variable. So the same is here. So basically, it's a very extreme example. So there's some relationship which could be totally random. It's certainly not the zodiac sign. I hope we can agree on that. But basically, so the comparison distribution for testing this probability is the chi-squared distribution. And we have the chi-squared table on Canvas, like this. Here. So that's chi-squared. And the chi-squared, just again, in the same fashion as the F distribution, we're doing the same thing. So we have a certain degree of freedom. We have a certain p-value that we're going for as our critical alpha, our critical value, and we're determining that respective critical value, and that's somewhere here on this unimodal positively skewed distribution. And if our calculated chi-square exceeds this critical value, then we will reject our null hypothesis. Simple principle. It's a straightforward test. With some subtleties in a multi-level comparison. Good. Okay, this was this. So we have a nominal variable of independent. Yeah, these are the. Yeah. So comparison distribution to chi-square distribution. We have some caveats. It needs to be a nominal variable or categorical variable of some sort. It needs to be independent observations. So you can't just count repeated entries. That is important to keep in mind. So it needs to be cross-sectional at one point. you need to say, okay, so each count in my 2x2 table is independent of the other count in there. You need to have random selection, goes without saying, they need to be randomly selected. Please make a distinction, and I've seen that error, make a distinction between randomly sampled and randomized. These are two different things.
So what do you mean by randomized?
Randomized would be if you randomize them in each group, right? Then they are randomly allocated into each group. That's quote unquote randomization.
Like equally distributed?
If you would equally distribute them like in a randomized controlled trial, you would randomize them into either group. It's different from random sampling where you randomly pick from the large group. Then you have a minimum number of expected participants per cell. So there are different definitions, or there are different recommendations how many need to be in a cell, but it's like it should be at least as many as row and columns. So at least as many as you have cells contained in your table. So if you have the soccer player example, that's 2 cells expanded to 2 more, so it's maximum 4. So it should be at least, there should be no 0 count, there should be no very low count in either cell that you're populating. But we will see in a second what I mean with that. Good. So then we need the degrees of freedom. That's again simple. We have a quote that hypothetically sum of squares. It's basically the number of rows here indicated as k rows minus 1 gets us the degrees of freedom for the row. It's just like an override. K of the columns, the number of columns minus 1 gets us the degrees of freedom column. We want the degrees of freedom for chi-squared. This is the degrees of freedom row multiplied by the degrees of freedom of column. So it's basically straightforward. And so it is being read from the chi-squared table. Once we have this degree of freedom for chi-squared, which is degree of freedom of row multiplied by degree of freedom of column, basically we're just finding it, then we're going to the acceptable alpha level, and we have our corresponding critical value. So it's straightforward. It's basically, it follows the same outline as other hypothesis tests. It's nothing new really. So that's an excerpt of this chi-squared table. Please use the one that I have provided you. Okay, so if we have now a soccer player example, how many degrees of freedom do we have? We have hypothetically now 2 observed minus expected. So there's 2 minus 1. Then we have 2 as the rows, that's 2 minus 1. 1 multiplied by 1 is 1. So our degree of freedom here would be at 5%, would be actually less than what's indicated here. So Nolan and Heinzen provide this as 3.841. We don't even have this on our chi-squared table. Reason for that is because commonly outside in the world, when you do analysis, you would use a different test. You would not use a chi-squared for this kind of comparison. But that's a different conversation, please. But here on here indicated by Nolan and Heinzen is 3.841. Good. So how do we calculate this? And this is the calculation of the chi-squared, and that's the heart of today's example. So we have now this formula, and let's digest this formula for a second. It's not that complicated. It's really considerably simple. So chi-squared is calculated as the sum of observed minus expected squared divided by expected. What does that mean? So you have now observed minus expected is O minus E is here observed minus expected. That's 24 and minus 24. Okay, simple. So now we have observed minus expected squared. That's nothing else but 24 squared. That's 576. But you need to first divide it by, so this is now observed minus expected squared divided by E is now this divided by expected. And to compute this, our chi-squared here is basically the sum of these two. So our chi-squared here is 41. And we have now a critical value of 3.841 is here significantly exceeded by 41, right? So that's the simplest of all examples. We're building here exactly these calculations that Nolan and Heinz to show here. They're coming now dramatically exceeding our critical value. So that's the simplest of all examples you could think of. But I just don't want to spend too much time on that because we're getting now to another one. We're getting now to a little bit more of an advanced one, and this is really money. And we have 35 minutes to get through this because this is an important concept to basically get to understand chi-squared. So again, same 6 steps. You identify populations, compare distribution assumptions, state hypothesis. The hypothesis here is that there's no association between dependent categorical variable and independent categorical variable. Research hypothesis is the inverse of this. Determine characteristic of the distribution. This is where we get the critical value. We determine critical values. Yep. We calculate and decide. So now our well, let us look for the example. So this is our first example. The second example is this one, and that's a little trickier. And this is why it's a nice example. So we're doing a so-called recycling study. 159 people. You know, when you go to Starbucks, again, so now right now you go in a coffee shop and you get your coffee, you get a coffee cup with your name on it, right? In many cases, this is the case. So in a recycling study, 159 people were randomly assigned to one of 3 groups. That is our independent variable. So either the coffee cup had your name spelled correctly, had your name spelled incorrectly, or had your name not on the board. So these 3 levels you have of your independent variable. Your dependent variable is now your outcome, which is your observed count. So either your coffee cup ended up in recycling, or it went into the trash. And the interesting psychological idea behind it is that if you see your name on a coffee cup, you may be more likely to recycle it rather than throw it in the trash. So now the question is, how do you test this, right? How do you test this? Just think for yourself, like, would you rather recycle what has your name on correctly?
I would think what you do.
You don't think?
I would think there's any connection, but I guess.
Well, subconsciously I could see that, right? A priori, without looking at the data, I could see this association. But yeah, it doesn't matter. Okay, so we have now a couple of things to do. So it was a randomized study. That means the count in these 3 allocations need to be identical, right? So they were, if we're summing this up now, that should be 3 times the same count, and it was 53 individuals with a total of 109. Total. So 159. 159 individuals got randomized into these 3 groups. Now we also need to understand how many did throw their cup in the trash and how many did keep it. So just with the naked eye, it seems like or more than double ended up in the trash.
Make it bigger.
Yes. Sure. Okay, so more of those cups seem to have ended up in the trash. So is there an association between your assigned 3 groups or not? So again, this is 2 different categorical variables, right? So you were in either of these 3 groups, and your outcome was either that or that. And so now first we need to understand what is now expected.
what's that third? Isn't that the third? Like 53, 53.
The 52.
But on the side, what's the?
No, this is the actual count. So these are the so-called marginal totals. The marginal total. So this is the sum of all recycled cups. This is the sum of all trash cups. So now when you do, when you think about it, if you would not see any difference between these three groups, you know the outcome, you know how many were the trash. But if you would not know the assignment to either group, what would be the expected count? Exactly, it would be equal between all three groups. So the way you would calculate this would basically be 52 divided by 3, correct. Exactly. And that would be the same for all your three groups. So that would be your 17.33. Equally, it would be the same for your trash groups, right? It would be the same. It would be this divided by 3. Oops. This divided by 3 would again be equally distributed. So you know the outcome and you equally distribute them based on what you would expect. So now we are now again aligning this. I'm just bringing it again in long format because that's our expected. And if you want to calculate and compare this now against your observed, so this is expected, and this is now observed. So your observed just needs to come down now from the 2 by 2 table. You just need to copy this down. And that's basically your observed versus expected. So from that point on, it's the same calculation as we have just done before. So now you want again observed minus expected squared and summed. So it's the same exercise. But first we need the degrees of freedom, right? So we have degrees of freedom. We need first critical value. So degrees of freedom of row, degrees of freedom of column. So degrees of freedom row is 2, right? So it's 3 rows minus 1 is 2. And degrees of freedom of column is 2 minus 1 is 1. So degrees of freedom here is 2 multiplied by 1. That gives us degrees of freedom of 2 for our critical value determination. So 2 at p-value of 5% gives us 5.99. This gives us here that 5.99. So this is the way you have to look at it. So you have the chi-square distribution. You have a critical value of 5.99. So now if we are calculating now the chi-squared in the same fashion we've done before, you basically have to calculate now O minus E squared divided by expected is now observed minus expected squared divided by expected. It's simple, right? It's a considerably simple calculation. And all that needs to be done now is basically to sum this up to get your chi-squared. And with 7.6, this is significantly exceeding our critical value.
Can you show on the table how you do it?
On the table.
Like on the chart with the chi-square.
Yeah, so we have degrees of freedom. Oops. We have degrees of freedom of 2 for the rows, with degrees of freedom of the column of 1. 2 multiplied by 1, so this is df.
How do you get the degrees of freedom of the column?
chi-squared? Well, let's 2 columns, -1. Okay, let's spell it out. 3 minus 1 is 2. 2 minus 1 equals 1. Degrees of freedom is 2 multiplied by 1. That's 2. And then you just need to go into your table, finding 2, 5% alpha, that's 5.99. Okay. So critical chi-squared, 5.99. We're rejecting the null hypothesis, and we find that there's an association. So that's how you would approach this. It's simple, right? It gets now a little bit more interesting when you basically, okay, so this other calculation we just did, we're exceeding. So now, and we're not doing this here. So basically what you could do, and statistical software will do that for you, they will basically capture and calculate adjusted standardized residuals of your observed minus expected differences. So they're basically calculating a standard error of your deviations and dividing these differences actually. But the standard error gives you adjusted residuals adjusted for the frequencies and the expected frequencies in the light of the column rows. But we're not doing this. The only thing we're calculating is Cramer's P of phi, which is basically here, the Greek letter phi, calculated as the x chi-squared divided by the sample size multiplied by the degrees of freedom. That is a marker for the effect size in the chi-squared, which obviously is also dependent on your sample size and your number of different observed counts. So if we do phi, this is now basically chi-squared divided by the sum of all these observed counts multiplied by your degrees of freedom, which we know is 2. You have here phi of 0.02. You need to put it in the square root, SQRT. Gives you a phi of 0.15. So now you have guessed it, there are also conventions. So you have now conventions to be read from different degrees of freedoms of chi-squared. We have degrees of freedom of 2. We have 0.15, we have a small effect size. So there's a small and significant effect of putting a name on a cup, of whether the cup ends up in the trash or goes in the recycling. That is kind of a fun example, right? Because it's an example where, for example, if you have a large domestic, national, multinational coffee chain, and they start putting your name, the name of the customer on a cup, increases the probability of recycling. So now the next step would be to actually ask one of these coffee companies, do you actually see that in the amount of recycling? Or, because you can essentially, every company would measure the amount of recycling because they're being charged for that. They're being charged for trash, they're being charged for recycling. So hypothetically, you could bring this hypothesis that we have seen in your little RCT to the test by approaching a large multinational coffee company and ask, once you started that practice, have you seen a step change in the amount of recycling garbage waste that you have? So it's kind of an interesting example that you could hypothetically in sustainability, which becomes now more and more important because all corporations want to go more quote unquote green and be more environmental conscious for very good reasons, obviously. They do look at these data. And that's actually an interesting example in that regard of what can actually be done by a corporation of that size. So now you want to also understand what are the respective probabilities? Which of my probability is actually, which of my interventions is basically causing most effect? And you can do this by basically calculating a quote-unquote risk or probability. So if you are interested, what's the probability of something going into recycling? You basically can calculate this for the count in each of these groups. So for all of these three levels that you have in your 2x2 table, you have here you have the possibility to calculate the probabilities of side. Okay, so if you want to know the probabilities of something going into recycling, probability of it going into trash, you can do this easily by calculating the individual entry that went into recycling divided by the overall number of cups in that group. So that's the easy calculation to do that. So you basically get 47.2, 24.5, and 26.4. If you want to calculate this for trash, this needs to add up to 100, obviously. So it's 28 divided by 53. Even if there was a correctly spelled name on it, the probability of this cup going into trash was still 53%, which is quite, so to say, a post hoc test, right? So if we're repeating this now for the other three groups, this probability increased substantially. So now you're interested, is my approach actually helping? If I have a correct name on my cup, does that make a difference? You have 47% versus 24% and 26%. So actually, when the name was incorrectly spelled, the probability of this going into the trash actually increased, which is also an important insight, right? You think about it in a more global scale. So the way you can test this is by calculating the so-called relative risk. A relative risk takes basically of two of these levels, the probabilities, and compares these respective probabilities. So if you want to know if you're more likely to recycle, if people are more likely to recycle their cup if the name was correctly spelled as compared to no name on it, you can do this by calculating the probability of that cup going into recycling in the group with the correctly spelled name divided by the probability of not having a name on it and going into recycling. So the relative risk here is 1.79. What that means is, and this is the interpretation, and those of you who may go into healthcare analytics, you can do this with whatever outcome you're looking at. If you're looking at death or hospitalization, you would express it in the very same way. So the probability of recycling is 1.79 times probability of recycling with a correct name is 1.7 times that of a cup with no name. So that's the interpretation of a relative risk. And that's important because not only is this 1.79 times that of a cup with no name on it, it's also a risk increase of 78%. So you basically a probability increase of 78% above the standard reference level. Any questions on this? So that's relative risk. It's quite important to know, at least in broad strokes, what that is. You can also graph this out, and we have talked about bar graphs. So you basically have here proportions that you are depicting, and you can basically show these proportions as a bar graph, and depict them next to each other with recycling or trash. That's a very nice way to depict this data. You can also do this next to each other, which comes to the same. You can do the simpler, you can do this more complicated. And with relative risk, you can actually calculate, as said, the ratios between one probability over the other probability. If you would like to show this right next to each other, you can simply do this by insert and take on bar graphs. Should be right here. Here, right next to each other. This. So you can do this quite simply in Excel. I didn't try this before. Yeah, oh yeah. Was the wrong. Okay, so this is the bar graph that would basically show you these different groups. You can now also bring over the labeling for these three different groups. And now you can use this for the labeling. Select data. Gives you now this. Okay, so this is how you would basically build such a bar graph, right? And that's the beauty in Excel. That's quite easily done. You just need to arrange your data in a way that basically allows Excel to understand what you want to do. So this is our recycling example. Simple, right? Okay, so this was basically so that's basically how you would show this as bar graphs. I also included any questions to any of this. I think that was simple, right? It's really important that you understand all the components of it. So you need to understand how to build the expected ones and then calculate the differences. That's considerably simple. Then from there, you basically get to a chi-squared. The chi-squared, you hypothesis test against the critical values. So you basically know the critical values based on the degrees of freedom. Same scheme, same approach. You can then quantify the effect size as grammars V of phi. Gives you a strength of this association, gives you an idea of how strong is this association. You can then calculate the proportions, the risk of each condition to be met in each of your levels of your independent variable. And then lastly, calculate relative risks based on what you have seen. So if you look here at these associations, so you know that these associations are here significant. So it's basically preserving a high probability of trash, but this substantially decreases with the name spelled correctly on it. Good. Lastly, so there's an R script. I just want to talk about this very, very briefly. Reason for that is it's not in a practice lab. I just want to show you that graph because R also can do chi-squared, obviously. And if you calculate, if you run only line 1, you get this table. You can now label the core names and you get here the very same table. So the outline of the table is always the same. Keep in mind, if you have a dependent variable, your dependent variable is the outcome. The dependent variable is whether that cup went into recycling, went to trash. That will always be on top. So you label the columns, what's the outcome. Then you have 3 different levels of the independent variable, which is correct name, incorrect name, or unlabeled. And these 3 will go into the rows. And the way you would approach this in R is considerably simple. You have an x chi-square, calculate this chi-square dot test. That's line 6. That basically just creates for you an object. And this object contains all the information you want from your chi-squared. So you can now extract all kinds of different information. If you just run chi-squared, you get the same answer that we had before. So we got a chi-squared of 7.6. With the decrease freedom of 2, you get a p-value of 0.2, which is an exact estimate. You can now explicitly with the $sign, you can address different things, observed versus expected. The expected is consistent with the expected we determined, right? The residuals are now these adjusted residuals that basically calculate for each of your cells. And it's quote unquote standardized adjusted residual deviation from what's expected, which takes into account the cell number, the frequency within the group. And with the standardized residuals, these are basically, these are the residuals calculated, and the standardized residuals are actually those that were standardized for deviations of the number of entries in each cell. Good. Any questions? If no, we can briefly talk about the question that Sophie has shown. Have you posted it to the discussion board?
Oh, I didn't. Should I post it?
So the question was, no, it's actually, I think it's easily answered because in the regression example, yes, I think it was number 16. You find it. Let's go another Villanova. Back to the version. Here we go. So the question there was, it was about the residual error or the error that you see in your estimate. If you want to quantify error, and this question also, and I thought it was clear, but just to recap, we have error, and this error is basically quantified in, there's a very good slide in that regard. This quantifies it quite nicely. If you are only quantifying the error in a prediction of the dependent variable, the regression score, by using the mean of y, which is one flat line here, your error is here quantified as the sum of squared deviations. So this is how you have to look at it. You have individual points and you have one mean. And the deviation from that mean to the individual point, this is your deviation. You're squaring this and summing this up gets you to the sum of square. The sum of squares error for this prediction only using the mean is the total error. And so now the question became, if I am quantifying now my residual error, so I'm employing my regression model and I'm estimating the individual point. I'm estimating Mr. Smith, who had how much with my function. I estimate Mr. Smith, who had one stressful life event, who then scored at 24. My prediction, my model predicts that this individual had a regression score of 12 or 13. There's a certain deviation from what I predicted and what we actually observed. And this is the residual error. This is this error. And this is the leftover error after employing my model. And now I have, as a consequence of that, I have a predicted or explained error, or explained variability in my model, which is quantified as the R squared. And my R squared is here quantified as the sum of square total, which is the mean predicting my dependent variable. So the mean of y predicts the y, the individual y. That's the question that you've shown. And minus the sum of squares of this residual error divided by the sum of square total. So you basically get this, the difference between sum of square total and sum of squares leftover error, that residual error, is basically the amount of variability that is explained by your model. So that's the sum of squares of the regression. And the fraction of what is being explained of the overall variability, overall error, that is the R squared. And this is what those two questions are aiming for. If this is being explained at that question, that answer, I'm giving 4 points.
So R squared represents the error that would occur?
No. R squared is the amount or the proportion of what has been explained by the regression model as a proportion of the overall error. So this, what has been explained, that's the sum of squares that the regression model has explained. That is the leftover error after that regression model was through. So you have the model through, and these differences from the model prediction and the individual observation, that's your residual error. That's this error. And the difference between those two, that's the explained variability. That's what the model has explained. Which, if you remember, in the multiple regression, which was the third example here. Did we do that? If you have, no, we didn't. If you use the multivariable model, this R squared, it tremendously increased because we're explaining more. So that's when the model explains more variability. Does that answer your question? Well, it's well explained. We talked about this in detail when we calculated it. Maybe rewatch the recording. Yeah. But it's clear. It's like it's 3 different entities that kind of intertwine, and the R squared is really like this overall estimate of this explained variability.
So I'm a little nervous about them.
Don't be nervous.
No, because I don't know if I did. The